And here is lecture 9. So in this lecture we are going to be talking about active filters. These are filters that involve resistors, capacitors, and operational amplifiers. And then we'll talk about cascaded filters, which is a way to get more degrees of freedom in your filter design and to get better suppression of the noise components that we want to reject. Okay, so last time we talked about passive filters that become frequency. These are circuits that are frequency dependent and will pass certain frequency components and stop others based on a configuration of resistors and capacitors only. So we talked about low-pass filters and high-pass filters that are passive, and we also however, now what we're going to do is we're going to generalize the resistances in op-amp circuits to frequency-dependent impedances. And what that's going to do is give us active filters, and we'll see that these give us some additional degrees of freedom compared to passive filters, in that we can add gain to our filters now. The simplest example of this is an inverting amplifier. So whereas we would typically have an input resistance and a feedback resistance in an inverting amplifier, now we can generalize this concept so that we have input and feedback impedances. So this will be, Z sub I, the input impedance, will have a feedback impedance, Z sub F. Here's our op-amp. To V out. And so this guy has a transfer function that's given by minus ZF, minus ZF divided by ZI. So for example, what we could do is we could plug in a parallel resistor and capacitor in the feedback loop, and we get the following circuit. We would use an input resistor, and then we would have two elements in the feedback loop in parallel. We'd have a capacitor, and we'd have a resistor. Jeez, that looks terrible. Hopefully you can see what I'm trying to draw here. My pen is crapping out on me. Okay, so this is, we'll call this capacitance C1, we'll call this resistance R2, and we'll call the input resistance R1. So then again we have V out on the left, and V in on the left and V out on the right. So the transfer function of this guy is going to be minus ZF over Z1, or Z in, is going to be the parallel combination of R2 and C1 minus that divided by R1. And if you work that out, what you get is R2 over R1 minus divided by 1 plus J omega C1 times R2. Right? So interestingly, it's only the components in the feedback network that actually determine the frequency dependence of this filter, right? And the input resistance only determines the scaling, this overall scaling of the transfer function. Okay, but we can see by just by looking at this that this is going to be a low-pass filter, right? Because when you have omega is equal to 0, this term just completely vanishes, right? And you're just left with R over R1. So your input signal is, that should be R2 over R1. Your input signal is scaled by this factor R2 over R1. Whereas if omega is very big, then the whole thing starts to go to 0. So this is a low-pass active filter. Okay, so let's plug in some real numbers here. So let's say that R2 is 56 kiloohms, R1 is 10K, C1 is zero point 0.1 microfarads. So if we plug all this in and work out the math, we would get that the transfer function is 5.6 divided by 1 plus, 1 plus 5j times 5.6 times 10 to the minus third times omega. Right? So that's still not totally intuitive, although we can see that it is a low-pass filter. But if we look at what happens at DC, of course, the bottom term here goes to 0, as I said earlier, and so we're left with an overall gain of 5.6. Sorry, there should be a minus sign there. Left with an overall gain of 5.6. And at omega is infinity, we have that this term dominates. It goes 1 over, it's essentially 1 over omega. If omega is infinity, 1 over infinity gives us 0, so it's going to be attenuating signals at those frequencies. So if we plot this guy, just like we did for the passive filters on a log-log plot, then what we'll get is this kind of shape. So if this is 0, then this is log omega, and this is log of h of j omega. And we denote, we have sort of these, again, these three regions. We have the zone 1 here, that's like the pass band, the frequency components that will be passed. This is zone 2, that's the corner region, and then we have zone 3, or the stop band. Sorry, zone 3, or the stop band on the right. Now the main difference between this transfer function and a passive transfer function is that in the pass band we can have a gain now that's greater than 1. You could also have a gain that's less than 1. But for a passive low-pass filter, you cannot control the gain. It will always be, on a log plot, it will always be 0 or 1 on a linear plot, right? You cannot actually control the gain of it. So we've gained a degree of freedom by building this with an op amp, in that we can actually amplify the components that we want to pass at the same time. And so obviously you can see that this is a low-pass filter, right? And again, we have, like we did for the passive filters, we have this region where the magnitude is dropping approximately linear on a log-log plot. And you can see that if you write down the general form for you can see that it should be linear on a log-log plot. If we write down the general form for a low-pass filter of this type, which is going to be some scalar on the top over 1 plus j times b times omega. And if you take the limit of this as omega goes to infinity, so as omega goes to infinity, we get approximately minus j times a over b times omega inverse, right? Because we can start neglecting the 1 in the denominator here. And so that's what you end up with, right? So you end up with, if you take the log of that, right, of course you get a minus 1 in front in the magnitude, and so then it's going to be linear, right? It's going to be linear in omega in that case, on a log-log plot. Okay, so to drive home the comparison to a passive filter, let's actually do a direct comparison of the two topologies. So a passive filter would look something like this, right? We would have some input voltage. This is a passive low-pass filter. We extract V out. Here's V in at the top. And then we have our capacitance. And then we have ground. So we're measuring the at any point in time we're measuring the voltage drop across the capacitor. And the transfer function for this guy is h of j omega is equal to 1 over 1 plus j omega r times c. But for an active low-pass filter, we have a different situation. We have, here's our circuit. Here's our input voltage. Here is our output voltage. We have a C and an R, C and an R2, and then an R1. So this is our active filter. And its transfer function is going to be given by, as we saw in the previous slides, so h of j omega for this filter is equal to minus R2 over R1 divided by 1 plus R2 times C times j omega. Right, so functionally these two differ by the fact that we don't have a 1 in the numerator anymore, right? So we actually have this ratio R2 over R1, and we can actually use that to get gain, to control the gain on the output. Now, if the feedback resistor on the active filter is the same as the resistor in the passive filter, has the same resistance as a passive filter, then the overall shape of the filter's transfer functions on the log-log plot will be the same, but the active filter's curve will be shifted up on this plot by log of that ratio R2, the feedback resistance, divided by R1, the input resistance, right? So if we actually plot this, a comparison of these two, then we would get this kind of plot. So here's log omega, and here's log magnitude h of j omega. So the passive filter is going to intersect 0, and I'll draw its transfer function in this dotted line. And the active is going to, so the active is going to have the same shape, but it's just going to be shifted up by an amount equal to log of R2 over R1. So that is this value there. All right, and this guy is the active, and this guy is the passive curve. Okay, but they have the same corner frequency. So they have the same overall shape, and they both fall off with the same slope as we increase omega. But the active filter will be shifted up by a certain amount, log of the resistor ratio. So basically what we've done here is that by adding the op-amp, we've obtained a new degree of freedom in designing h of j omega in terms of this ability to scale it up or down. Okay, so that introduces active filters. So now we're going to talk about gaining additional degrees of freedom and better suppression of noise using cascaded filters. Right, so graphically, for a given signal conditioning problem, the typical filtering task is the following. You have your signal input plus your noise that you want to get rid of. You input them to some filter, say that that's filter 1, and now you're going to get filtered signal and filtered noise, and hopefully the filtered noise has a little less amplitude than it did when you on the left hand side. Okay. So let's say we have the following situation. Let's say that we have lots of noise at 60 hertz, but that our signal has no energy above 10 hertz. Right? So let's say that we've got our signal is pretty much all living down below about, this will not be to scale at all, but we'll say our signal's living all down less than about 10 hertz, and we have a bunch of noise at 60 hertz. Right, so if we actually were to plot, obviously in the frequency domain, these two signals, the signal and the noise, are nicely separated, which is why we can hope to filter them out. So this is like the Fourier transform of the noise, is this right curve, and this guy is the magnitude of the Fourier transform of the signal. So the goal of filtering is to suppress the noise, right? So we want to filter out the noise. And so what we might do is apply a low-pass filter in this situation, right? So you got your signal here, you have your noise here. So what we might do is we might apply a filter that looks like this, whose transfer function looks like this. Right? So it basically is a low-pass filter that passes the signal, does nothing to the signal, hopefully, and suppresses the noise. Right? So this is our filter's h of j, magnitude of h of j omega. But with the types of filters we've shown so far, we might not really get enough suppression. Right? So what might happen is that instead of fully suppressing the noise, what we actually get is, sorry, I wanted to do that in black. What we actually get after filtering is still going to be some significant amount of noise, right? We'll have our signal here, hopefully untouched. Maybe we have some significant amount of noise left that is still degrading our SNR significantly. Right, so this would be our filtered noise after just a single filtering operation. And obviously, the closer in frequency the noise is to the signal, the worse this problem is going to be. And the difference between 10 hertz and 60 hertz in practice is quite small. Okay? Okay, so the question is that we might ask ourselves, given that we have suppressed the noise somewhat but not quite enough, is can we just add another filter in line to get better noise suppression? And the answer to this is yes, you can. If you cascade another filter on the end of the previous filter, you can, but you've got to think about what it's going to do to the overall transfer function of the system. So for example, let's say we're going to do this and put two low-pass filters back to back. So originally we had the input signal and the input noise. And then that guy goes into the first filter, call that just F1. And then now we have our filtered signal and our filtered noise. And so we're literally going to just connect the output of the first filter to the input of the second filter to get a cascaded filter. So we'll get filter 2, and then out of that we'll get our doubly filtered, sorry, that's supposed to be an arrow, doubly filtered signal and doubly filtered noise. Okay? So let's give a concrete example of this schematically. Let's say that we're going to cascade two active low-pass filters. So we'll have Vn on the left here. It will go to one low-pass filter. And then out. need to draw a capacitor here as well. So we'll say that this is C1 and this is RF1 for feedback on the first one. Then this will just be R1. This will be R2 on the input to the second one. Then we will have a capacitive resistive feedback on the second guy. Which will take us to V out. And so then we'll call this guy RF2 and C2. Right? Okay, so what is the transfer function for this guy? Well, it's just the product of the two transfer functions for each one, right? Because you take the input signal, because the transfer function for this guy relates the input signal to the voltage here, right? And so then the second transfer function relates the voltage here to the voltage here. And so to get so if you take the expression for what you get here as a function of here, then you plug in the expression for this as a function of this. Then it's the a Vn. Then it's a then you just multiply the two transfer functions together, right? So the overall transfer function is going to be 1 over R1 times R sub F1 divided by 1 plus J omega C1 times RF1, right? And we're going to multiply that into 1 over R2 times RF2 divided by 1 plus J omega C2 times RF2. Okay. So earlier we saw that as omega goes to infinity, the transfer function of a single low-pass filter looks linear on a log plot. And this is because as omega goes to infinity, we have that this quantity A over 1 plus J times B omega is approximately 1 over J times B, sorry, A over J times B times omega inverse, right? Because as omega grows, it becomes much, much larger than 1, and so you can neglect the 1, and then you end up with this, right? And if you take log of this, then you just get minus omega, so that it's going to look like a straight line on a log-log plot. Now, if we cascade two identical filters, we're going to get something like the following. We're basically going to get that as omega goes to infinity, we're going to get something like A, that the transfer function is something like A times JB times omega to the minus 2, right? So we're going to have omega 1 over omega squared, and when we take the log of this, we get a minus 2 in front instead of a minus 1 as we do with a single filter. So it's also going to be a straight line on a log-log plot, but it's going to have twice the negative slope of a single filter. So this filter, we can rest assured, will indeed succeed in better suppressing the noise. But the problem is that at the single filter's break frequency, right? We can define a break frequency for each of the individual filters, and at the original single filter's break frequency, the gain will now actually be a little bit lower, right? Because we're squaring the transfer function, and so now instead of getting 1 over root 2 at the break frequency, we actually get something smaller, which is 0.5, or 6 dB down rather than 3 dB down, and so we're going to have to take this into account. So, for example, if we had on a log-log plot, where we have the x-axis is log omega and the y-axis is log of magnitude of h of j omega, comparing the transfer function of a single filter with cascaded filters, if the original filter has this sort of transfer function, with the cascaded filter is going to be mostly the same in the passband, but it's going to go down. It's going to start to go down earlier, right? So its 3 dB frequency is actually going to be at a lower frequency than the original filter, and so we have to take this into account and actually possibly once we cascade two filters together, then we have to push both of their corner frequencies maybe a little bit higher, so that you don't attenuate your passband too much, right? So you can see that whereas, so here is the one filter, and here is the two filter response, and you can see here that if this is the minus 3 dB point, that it happens at a lower frequency for the two filter than it does for the two filters than it does for the one filter. So we have to take this into account, as I said, to make sure that we don't over attenuate. To make sure that we don't over attenuate the low frequencies, right? So basically, what you would do is you could possibly duplicate the single filter twice, right? But then you could actually adjust the resistance or the capacitance such that you push the corner frequency a little bit higher, right, back to where you originally wanted it to be. Okay, so let's do a specific example of this, of cascaded amplification. So let's say that we're doing an electroencephalogram, EEG sleep study. And so in this study, our signal is described as the following. So we have these delta waves that we're trying to measure, and they have frequencies around 3 hertz maybe. And then we also have these other signal components we care about down to about 1 hertz. So our overall signal region we care about is about 1 to 3 hertz, right? So and then our RMS signal is going to be about 5 microvolts, right? That's very small. On the other hand, then our noise is at about 60 hertz, so it's a little ways away from the maximum signal frequency we care about. But the noise RMS is huge; it's 5 volts, right? So our time domain, our SNR, is going to be 5 microvolts divided by 5 volts is 10 to the minus 6, right? That's horrible SNR. So what we will always do in these kinds of situations is first apply differential amplification, right? To try to suppress this, because we usually have the same 60 hertz noise on both the plus and minus terminals of our transducers. But let's say that we did that and it only brought our SNR up to about 1, right? Which is still unworkable by our own definitions, right? Earlier we said that it's better to have an SNR maybe around like 20, but it kind of depends on the situation. But certainly in almost any situation you can imagine, an SNR of 1 is not going to work. Okay, so let's say that we will accept an SNR of 20, but we also require that the transfer function amplitude at 1 hertz, right? So this is the amplitude at 1 hertz. So to get omega from 1 hertz, you got to multiply by 2 pi. So this is the transfer function magnitude at 1 hertz. And let's say that we also require, as part of our specifications, that this guy must be no more than 20% different than the transfer function magnitude at 3 hertz, right? So you can imagine here that because we've got the signal at a lower set of frequencies than we have our noise, that we're going to end up wanting to use a low-pass filter. So we're going to have we run into the risk of possibly over-attenuating the 3 hertz signal. So we got to watch out for that. Okay, so again, for this problem, we're going to need a low-pass filter, right? So you might first try a single filter with a corner frequency of about 3 hertz, right? And so if you do this, then you're going to get a transfer function amplitude at 1 hertz of 0.949. Okay, fine. But then at 3 hertz you have 0.707, right? That's your corner frequency. We specifically set it up this way, right? So if you compare these two numbers, you can see that you have a greater than 20% difference between the two. So we have greater than 20% difference between those two. At the same time, our SNR is quite bad, right? So we have an SNR of 14 here, right? An SNR improvement of only a factor of 14. So that's not going to be good enough, right? So that we get that by evaluating the transfer function amplitude at 60 Hertz and looking at how it compares to that at 3 Hertz. But of course that doesn't meet the specs because we met neither our 20% difference spec nor our SNR spec. So let's say that we try increasing the corner frequency to 4 Hertz, but still using a single amplifier. And so now at 1 Hertz we get 0.949, and at 3 Hertz we get 0.82. Okay, so now we are actually in spec for the 20 Hertz. So now we have less than 20%. I'm sorry, we're in spec for the 20% difference. So we have less than 20% difference now between the frequencies. And however, we now actually have an SNR only of 12. So we've worsened that scenario. So it seems like there's no way to win here with a single filter. So what we're going to do is cascade in a second filter, right? So now we're going to add in a second filter, and let's say that now we get that the transfer function amplitude at 1 Hertz is 0.949 and at 3 Hertz is 0.53. Now the 60 Hertz signal is hugely suppressed, so that's great, right? So now we have that the SNR, the difference between in the passband is definitely greater than 20%, right? And because 0.949 minus 0.53 divided by 0.949 is a lot bigger than 20%, right? It's more like 40%. Okay. On the other hand, though, we have dramatically improved our SNR. Now our SNR is like 200. So our SNR is great. It's much better than it has to be. So now what we can do is we can go back and we can back off the center frequency, or the corner frequency, so we can actually shift it. We can actually increase it so as to improve the difference between these two, reduce the difference between the 1 Hertz and the 3 Hertz signal by trading a little bit of our SNR, right? Because this SNR is way bigger than we need it to be. So we can trade some of that to get a smaller variation across the passband. So when we do that, we get 0.949 at 1 again, 0.81 at 3 Hertz. And so now we are in spec, right? Now we're in spec on the 20% difference. And we've given up some SNR, but it's pretty darn good at 81. Okay, so this is in spec now. So as what we've described here is kind of a rough procedure for setting these up, but we got the job done pretty well. And overall, this circuit could do a pretty good job of getting a good enough SNR that you can now put it in a computer. You can now sample it with a computer, and you won't be wasting all your dynamic range on sampling the noise. And so then after that, you could do some very simple digital filtering, and really get the SNR very high. Okay, so that concludes this lecture. What we've talked about is active filters, which give us more degrees of freedom in tailoring our transfer functions. And we've talked about cascaded filters, where we stack multiple filters end on end. And what we can get with these is better suppression, but we have additional considerations that we have to think about in terms of the shape of the overall transfer function, and how to set the corner frequencies then of those cascaded filters to get the overall performance that we need from those circuits.